CTO of Rumblefish. Rumblefish is a small development shop in Poland. We have 30-something developers, and I've been in crypto for 9 years, and especially in EVM. So wanted to be here, but he is from the other part of the globe and like couldn't travel. So what is this project about? What are we trying to solve? We are trying to solve the problem of prediction markets, which currently need accurate data, and as things are being done today, the resolution of a certain event is just centralized, and these markets are prone to manipulation by whales, or even outright fraud and corruption by just people who have admin access, proving the opposite of the actual resolution. And this limits the usability of these systems. You can only trust them until a certain TVL, because there is always enough money that if it's on the line, it will be enough to corrupt individuals who are admins and just like rug pull or do something. So what we are trying to solve is shift where the trust relation is from admins to, well, I will talk about where. So so what we want to do is we really want to allow Ethereum to read the news. Right? This would be ideal, that just like ideally, we would introduce a new opcode, which is like ChatGPT, and you just put in the prompt and get resolution, and this would be making our project, unnecessary. But obviously, this is not going to happen because calculating LLM inference is a huge computation. If it were done by all the verifiers, like this would just blow up Ethereum. This is not going to work. So this can be done in a sort of like a L2 fashion, where on L1 we have sort of like a registry of events that we're interested in, and like some information about the process of resolution, but the computation itself, so the LLM inference, has to be done off-chain and proven in a cryptographically sound way. So this is a little bit how we envision the process. So there is some kind of registry like we have in existing systems, like in Polymarket and in Numa. There's a registry, and people just produce information that they're interested in a certain world event. In this example, there is an interest about football game of FC Barcelona, and then this event actually happens, and there is some reputable source of news published on the web. And this is really where we want to shift the trust relation, so that if there is an article on the web and it's on a HTTPS, so there is a possibility to grab information about the session using TLS Notary. I don't know if everyone is familiar with this project. This is a project from Ethereum Foundation, and we are like making very good progress. This is not something that would have to be done by us. This is the most important thing. Like, we wouldn't have to be a trusted party notarizing the TLS sessions, because there is a widespread effort to, make this work, and we can, build on top of giants. So what we really want to do is that there is sort of like a network of, let's say, nodes, and they observe the news specified by the registry of world events, and then they, like when the event actually happens and the news is published, they notarize TLS session and upload it to data availability layer, so that other nodes in the network can actually verify the data. And for DA layer, we choose Celestia, which is a project you may know about or not, but this is sort of like another blockchain, and you can verify on Ethereum that a certain blob has been published on Celestia in a smart contract. And then the idea is that, like, using this TLS session, we can actually combine the description of world event with a text extracted from the news article, and we can construct a prompt, and then this prompt can be run through LLM, and LLM, if like instructed correctly, can give you a yes/no answer, or can give you a more, let's say, detailed answer. Maybe you're interested in a score or something more, particular. But this is all just LLM engineering and not, subject of this talk, but much easier than the cryptographic part of it. And after this is all done, we just want to produce an attestation on-chain so that other systems can just use this attestation to resolve their, events. This is the big picture of the project. So this is what we want to solve. Now I will tell about how. So how proofs can be done and how they have been done historically. So there is approach of using interactive protocols and non-interactive protocols. So example of interacting protocol, for example, is Arbitrum, like how they resolve blocks on L2. Essentially, they have a full history of execution, and when you want to resolve something, you produce optimistic resolution, and other participants on the network can challenge your resolution. And when they challenge your resolution, there is always agreement on the initial state and disagreement on the final state. And then through interactive protocol, you just bisect. You make the range of disagreement smaller, 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 until it's only one step big, and this one step you can replay on chain. This is a typical implementation of interactive protocol. And it's cool because it's very flexible and allows for proving complex computations. But I mean, you may ask how complex? Like really sky is the limit. Like you can make many iterations, and really every iterations you add, you double the size of your computation. So this really can be used to prove very complex and long computations. But obviously, this interaction is complicated from the crypto economic point of view, because you have to have some time slot for every interaction. And then if you are a party who want to derail the system, you can just stop interacting. And we have to wait until we decide it's a timeout. So if there is like many interaction steps, it may take weeks to resolve. And this is just not ideal. If you want to have predictions markets, which should react fast, we cannot have like a week of waiting. So some aspects of it are very cool, but some not so much. And then there are Starks, and Starks are great. And really, if it were possible to just import Llama CPP into RISC-0 and just run it, like we wouldn't be doing this project, and I wouldn't be doing this presentation. But I think it's clear for everyone that this is way too much computation for a Stark to be able to sustain. Like this is probably in terms of like years of centuries for computation like this and witness to be calculated. So this is just not going to work. So what we are doing in this project, we are combining these two approaches and sort of finding a middle ground. So we will be using techniques from both, and we call it a naysayer protocol. So in naysayer protocol, we are kind of using a divide and conquer approach, in which we from the interactive protocol, we also have a settler produce an optimistic resolution, and what is addition is that we also have him upload to data availability layer a set of intermediate snapshots. And I am taking a little bit of liberty here because I only have 20 minutes and I don't want to get into details. In reality, this is heavily compressed, but for sake of this presentation, let's just say this is just intermediate snapshots. And what we are able to do is that we can use the non-interactive approach to have a naysayer, so a challenger, prove that the transition from snapshot number n to snapshot number n+1 was invalid. And this invalidates the whole computation. So instead of running entire computation in a snark, we only have a challenger run a tiny part of it. And I will tell how this is accomplished. So first of all, what do we really run? So it is all based on Llama CPP. This is an open source project published by Meta. And like the llama name is confusing because there is a name of a model, which is llama, but also llama CPP is just sort of like a utility that you can load a GGML model, and it's not only llama model, which is published in this way. Also, DeepSeek is published in this way. So really, any model that is published as GGML file, we can load and run inference through it. So what we do with this, we compile it to RISC-V architecture because it's much easier to work with than Intel or ARM because it has much smaller instruction set. And we get an ELF file, like you all probably use Linux, so you are familiar with ELF files. And then this is our piece of software, a SnapVM. This is based on Unicorn, which is a well-known CPU emulator. And we just, load it as a ELF loader in, Linux kernel would load it. And then we run it. And when we run it, like the first thing that llama CPP does, it opens up the GGML file and loads it into memory. And GGML file is kind of big. I mean, it can be anything from 1 gigabyte to 10 gigabytes. So we need to run it for a while. And we also needed to implement system calls so that it can grab, model data. But then you may say, okay, but if it needs to read model data, like it is not going to be deterministic because someone can provide a different model data. And yeah, of course, this wouldn't work. So what we do, after loading model data, we just pause the virtual machine and we take a snapshot of it. And pretty much the entry point to this computation is a llama CPP, which was sort of pre-run only to the moment where entire model was loaded into memory and just represented in memory as GGML objects. And at this point, we are ready to make the inference. And this serves as a layer. Actually, I want to do this slide first. So this serves as a layer. So we sort of have our memory in initial state, where at some region of memory, we have a llama CPP with a model loaded. And then we overlay on top of this the data of word event and the artifact of TLS session. And all in all, like obviously this memory is way bigger than this Merkle tree. And in reality, we are not using Merkle trees, but something more complex. But I wanted this to be clear. But what is possible is that we only to validate the initial state, and this needs to happen on chain because there needs to be agreement on the initial state that this is correct. We only need to validate certain sort of subtrees of Merkle tree, so only a handful of paths needs to be validated to show that a snapshot to entire memory holds exactly what we needed to hold at the beginning of computation. And we do the same for word event and TLS notary. And then, going back to this state, the nice thing about VMs is that when we have agreement about initial state and we have rules of VM, like we know that the initial state determines completely the next step, which determines the next step, and ad infinitum, it also determines the final step. And there is nothing indeterministic in this approach. There is no multi-threading, there is no reading time, there is like all the things which typically introduce non-determinists has been just removed. So this is as deterministic as Solidity code running in the VM. So pretty much if we have agreement on the initial state and disagreement on final state, like we can just show where the error was. And there is always an error, there cannot be any disambiguity. And how do we prove a single step? Like this is a virtual machine. You are probably all more familiar with EVM, but this is pretty much a same approach. There are the program. The emulator has some internal memory which has program counter, all the registers of the CPU, and then the program counter points to a region in memory which has the instruction which is being correctly run. And every time you run an instruction, you just increase the program counter. Some instructions can just jump the program counter to some other location. But the point is that what we need to actually do in a Stark, proving a single step, is very, very simple. Like we need to, for example, here, instruction being done is just that you do a bytewise AND operation, between register A5 and the value 15, and then you put the result in A0. So the point is that if you wanted to run a risk zero Stark, demonstrating that some snapshot has correctly transitioned to another snapshot, we only need a very small data points. We need a value of program counter, we need a value at this memory address, we need these registers. 5 minutes left, perfect. And then, so we need to prove them. And to prove them, we are using Merkle paths, but we also, it's not exactly a Merkle tree, it's a Merkle tree sort of done in a way that we know which regions of memory are updated more often than the others, because registers are updated all the time, so they are very shallow in a tree. And we also know that the stack is updated all the time, so it's also kind of up the tree. But then, and another important optimization is that the program counter always points to just a code part of memory, and we already validated this in initial state, so we don't need to validate it over and over and over again. If we introduced another rule in our VM that just program cannot update its own code, which is an error if it were to try. So with this small corner cutting, we were able to really optimize it in terms of how many paths we need to prove inside the Stark. And when you have ability to prove a single step, like if you want to prove multiple steps, you just do the same but in a loop. Yeah. Okay, so this was a lot, and I didn't make a pause for questions. So maybe that's a good moment. Like, maybe there are some questions about what I shared.
How long does it take that initial snapshot when you get everything loaded in memory?
Well, initial snapshot is kind of fast. For us to generate initial snapshot, it took like, I think, 4 hours. And it depends on how big of a model we choose, because there are like many different choices of parameters and quantizations. But it's a little bit irrelevant because we only do this once, and we produce like a snapshot, and then it's just loaded as an initial state. But then the entire computation currently, it took us 17 hours to complete. And this is something that we are working on. And it's really about how Unicorn implements extended instruction set for vector operations. And I know it's a mouthful, but this is something we need to work on to like bring it back to a sensible times.
When you're loading up real-world data, do you take the previous snapshot and then load more data in, or do you have to do the whole process again of initializing the model? So like, let's say you have your snapshot from let's say 2 weeks ago, and there's been some football games. You want to add that real-world data onto.
No, so to make one computation, you take a snapshot and you just overlay it with the data you want. So there is no transition, no like learning, no remembering. So it's an isolated computation every single time.
We have 2 minutes.
Okay, so the summary is that what we are doing, like we want to enable close to one-shot validation of LLM inference. And with this approach, we can use LLM models which are big enough and smart enough to actually resolve real-world events. And yeah, like this is also important that what we are building generalizes to any computation. Like we sort of are interested in LLM, but this is, from our point of view, this is just extensive computation. So what we will do probably can be used for some other things which are comparable in complexity as inferencing LLM. And I thank you very much for coming to my talk and for your attention. And I hope you learned something interesting today, and it will like inspire you to do something interesting on your own. Thank you. Thank you.
So great. I think that we could go Is it here? Gahidner? Here? Because that guy is the next one. He will start. Oh, yeah, yeah, yeah. Pleasure, man. So you already have your slides?
I gave it the
You get it?
slides.